Hi, everyone. Every day, every hour, this very minute perhaps, malicious actors attempt to break into your software supply chain. Are you ready for that? September 2021, Travis CI flaw exposed secrets of thousands of open source projects. Very popular tool to build pipelines, exposing secrets, exposing credentials to access your private repository where you publish all your company packages, credentials to access production environments. It was a disaster. October 2021, popular JavaScript package infected with malware. Tens of millions of computers worldwide has been infected with a password stealer and a miner. Are you really sure that none of the third-party dependencies you include in your projects contain any malware? How can we spot that? November 2021, the log4j vulnerability will haunt the internet for years. Hundreds of millions of devices are likely affected, and many still are. There are still many applications out there published and supported by many different organizations that are still using vulnerable versions of log4j. The last estimate from last December was around 40,000 applications out there still using vulnerable versions of log4j. And what's next? Since 2021, so many things happen. We've been getting more and more supply chain security attacks. But what's a supply chain? Why do we want to secure it? A software supply chain is the set of everything needed to deliver software to production. And of course, it includes all the code, the dependencies, and the tools we use to build the software. But it also includes, and most importantly, it also includes practices and people. So it's not just about technology. Practices and people are really important. The people involved in any of the stage of the supply chain. The design phase, the implementation phase, the deployment phase, operations. Everyone is part of what we call a software supply chain. We can identify a few stages. We have the source code step, where we implement a new business idea. Of course, we bring along some dependencies, some third-party dependencies. We go through the build process, where we combine all these packages together. Eventually, we're going to obtain an artifact. An artifact could be a jar file, a container image. That's what we ship to customers, or maybe it's what we deploy ourselves if you're running a software as a service business. An important part here is that every step in the software supply chain has multiple security risks and impacts. Security, any kind of security, is all about managing risks. So we have to identify these risks and determine the impact for our own specific software supply chain. I'm going to talk about several tools today, several technologies, but tools are not enough. Sure, they're a really important part, but security is not a tool, security is not a product. We need the right practices in place to use those tools based on a certain strategy that we want to define, considering what are the security risks that we identify as part of our own software supply chain. Because there can be different requirements across different organizations. And the people factor is really important. We shouldn't forget about that. We need also an organization structure that can empower and facilitate people in doing the right thing when it comes to security. So even though I'm going to focus a lot on tools today, those tools alone will not work if we don't have consideration about what practices we are using for security and the people factor. I'm Thomas Vitale. I work as Systematic in Denmark. I'm a software engineer. I'm really passionate about anything Java and Cloud Native. I wrote a book combining all these passions of mine called Cloud Native Spring in Action. And I'm also a big supporter of open source technologies, try to contribute as much as I can, both in the Java space and in the Cloud Native ecosystem. So, supply chain security, where to start? Let's start from the first step, which is the source code. Now, when we start a new project, typically we set up a new Git repository. Now, raise your hand if you're not working with Git, but you're working with something else than Git for version control. Okay, that's interesting. Let's talk about that later. I'm curious. So we typically have some kind of version control system. Git is the most used one. And Git has a very interesting property that we really like, also from a supply chain security perspective, because it provides an audit trail of every change. So we can ask the question, who did a specific change? And of course, we get an answer out of it. But can we trust the answer from Git? Maybe not. Let's have a look. So I have a new repository here. So I want to work on a new application. So what I'm going to do is configuring some name and email, because I'm going to make changes and I want, let's use the email address that GitHub provides. So if you were planning to send me spam email, you have to find another way. I'm sorry about that. All right. So now I can start making some changes. I just configure Git with my name and email that will represent then the change that I make. So it will be connected to myself. Let's make some changes. Demo with Git. All right. Let's commit the changes like that and push. All right. So now I'm going to use GitHub for convenience to check that audit trail. Let's have a look. So we can see here I have a new commit updated now. That's great. We can see it was me making the change. Nothing weird about that. So now I can see Mauricio over there. So we collaborate a lot. So maybe he can help me building this application. And he would probably go through the same step. So he would, let's configure. So he would go through the same configuration. With his name, of course, and with his email. If I spell correctly, that's email. And then once again, users, no reply.github.com. And now also Mauricio can contribute to my repository, so I can make some changes. Demo with Git at Devox, and commit those changes to the repository. That's one of the power of open source, right? On GitHub, we collaborate and contribute to common projects. I'm really creative with these commit messages, right? So that's another update. And I have to push, of course. And now if we check the audit trail, we can see that who made this change? Salaboy, that's Mauricio. But something is wrong, right? You're all witnesses. It was me doing that. It wasn't Mauricio. So did I just hack into his account? I don't think I'm that good at hacking. So what happened there? What happened is that Git doesn't have a concept of authentication. So you can write whatever metadata you want in a Git commit. So if we really want to trust the audit trail here, we have to do something about it. Because as you can see, I mean, we even get a nice link to his profile on GitHub. That's quite convenient, but Mauricio didn't do anything on this repository. And yet, he's right there, mentioned as the author of that commit. So how can we fix that? Since Git doesn't have an authentication aspect into it, then we have to rely on some Git platforms like GitHub or GitLab. And one thing we can do to solve this problem is requiring commits to be signed. So we have to introduce some form of authentication. So if we add a cryptographic signature on a commit, then we can trust it more, because we make the audit trail trustworthy, because each user, each commit will be signed, and will be signed with a key associated univocally to that specific user. And hopefully we manage those keys correctly. We can use some GPG or SSH keys, but we can also use a keyless approach. So without having to configure any key. This is my favorite approach, using a tool like Git sign. However, GitHub at the moment doesn't support that, doesn't know how to verify those signatures. So I have to go back to the traditional Git signing with keys. That's a bit unfortunate, but hopefully things will change in the future. But the important part is we want to reject commits that are unverified. And we have to make sure that every time we commit, we add a flag so to sign the commits that we are pushing to the repository. So let's try that out. I'm still here. Let's make some changes to the repository. Now I can add the change to the stage and commit. And now I'm adding this flag, uppercase S. Now pay attention, there are two flags in Git. One is uppercase S and the other one is lowercase s, which stands for sign off. So one would think that, okay, that's what I'm going to use to sign. No, that's not for signing. So remember to use uppercase S, because the other one is used for other reasons. And now I can push the commit. Now I'm signing the commit, but of course I'm making changes from my own computer. I have Git configured with my own key. So what happens if we go on GitHub now, we can still see that Mauricio authored the commit, but that wasn't true. But now I get this badge unverified. So GitHub doesn't recognize that key used for signing as the one associated to Mauricio's user. So what I can do in GitHub is rejecting any commit that gets unverified. Now, if I switch back to my account, I would get something like this with this verified badge. At that point, I can trust more the audit trail. And this is all in relation to an important concept in supply chain security that is called provenance. Provenance is a proved and validated history of a software component across its supply chain. So we want to know where certain changes, certain components in our software supply chain come from. And we want to know it in a trustworthy manner. So it's not enough for someone just to tell us, yeah, that's what happened. We need a way to prove that that is an authentic statement about what happened. And when it comes to the source code and Git in particular, one way of doing that is signing the commits. Of course, it's not bulletproof. Nothing is bulletproof when we talk about security, right? So we have to make sure that we manage carefully the keys, if you're using the keys or whatever approach we adopt. All right. We don't work in isolation just with our own code. We typically use some third-party libraries. So we need to consider how to secure dependency as well. And in Java, we have really great tools like Gradle and Maven to help us not only build a project, but also to manage dependencies. Now, there are some basic features in both tools, but sometimes there are some hidden variables that might affect the security posture of our project. So what I mean by that? Let's ask the question, where are we fetching the dependencies from? Now, it might seem a trivial question. Yeah, probably from Maven Central. But in a real-world scenario, maybe in your own organization, you probably have some other repositories. You might have your own organization repository. Maybe you make an agreement with some vendor to access their own repository, to access some third-party vendorized libraries. Sometimes it's not that clear where we're fetching dependencies from. And when we do, which dependencies are we fetching? Because each dependency might have transitive dependencies, which might have transitive dependencies in turn, and so on and so forth. So are we really fully in control of all the dependencies that we're bringing in inside our project? And when we do that, it might be that one library is importing the same third-party dependency as another library, but with a different version. So how do we manage these conflicts when that happens? And there are some differences when we use Gradle or Maven. So if you switch between projects using these two tools, things will not work exactly the same. So we have to be more aware of these questions that, again, might seem trivial at the beginning, but actually they might hide some bugs in our strategy for securing the supply chain. So I'll just give you a quick example. I have a project here. I have a Gradle project using a Spring Boot application as an example, and I have two dependencies. Just two. One to build a web application, the other one brings some test dependencies. So far, so good. And then I have the repositories. I'm using Maven Central, so nothing special there. It's quite common. But let's say I'm in the context of my organization, and I want to access my own company repository next to Maven Central. So what I do is define a new Maven repository. I'll pass the URL. My repo something. That's great. So now I can access to my organization own packages. But what happens if I have the same dependencies in both repositories? Well, because my custom repository comes after Maven Central, then Maven Central will win. Now, in Java, we don't have too much this problem, but in other ecosystems, there is a type of attack, it's called dependency squatting, where upstream in some public repository, you might have a malicious dependency using your same coordinates that you use in your organization. And if you order these repositories in the wrong way, then you might get the wrong dependencies. Now, Maven Central is quite good at preventing that, so it's not much of a problem, but it's something to consider. Also, from a security perspective, again, I'm a developer. If I start having to deal with all these repositories and configuration and what comes first, it's not that good of an experience. And I might make mistakes if I have to do it for every project. So a typical approach, if you have a centralized team in your organization that manages this organization repository, is that you might want to use that as the central and single repository to access any kind of dependency. And then that team can be responsible for setting up some mirrors so that through your company repositories, then you also get access to Maven Central and other repositories. But then all the security concerns are centralized. And most importantly, as a developer, I don't need to worry about that. I just need to point to my own organization repository. But what about Maven? I have the same project in Maven, same dependencies. I have a Spring Web dependency and test dependency. Now I want to access my company repository. So let's do that. Let's add a new section dependency. No, it's repositories. And we add a new repository. Let's give it a name. I don't know, my org repo and the URL. Like that. So now the centralized team that manages this repository can also make sure that all dependencies flow through the repository. However, if you notice, there was nothing about Maven Central in here. And that's because Maven applies that automatically. So if I want to achieve the same result I just accomplished in Gradle, I have to remember to remove Maven Central from the list of repositories. Otherwise, I have a false sense of where my dependencies are coming from. So I have to explicitly disable Maven Central from here for all production releases. So we can say enabled false. And that's central. So that's just an example of some small differences between the two tools to consider when we really want to answer those questions in a trustworthy manner. But we still have one problem, though. We talked a bit about the first question, but how about the second and the third one? Can we get a full, clear, precise overview of all the dependencies we are using? There is a concept that we can adopt in order to achieve that, which is called SBOM, a software bill of materials. It's a list of ingredients for our application. And it should be a comprehensive list, so not just the dependencies that we see on the build Gradle file or POM XML, but everything that will end up in our artifact. So including all the transitive dependencies, which also make clear what kind of dependencies we are fetching in case of conflicts. There are different ways to deal with SBOM. Now, the most simple way we can define an SBOM is just taking, a document and write down manually the list of packages, but that doesn't help, right? So we want to do it in a more automated way. So there are two main standards for exchanging and defining SBOM documents, CycloneDX and SPDX. I'm going to use CycloneDX today because at the moment it has a wider support in the Java ecosystem, but you can use SPDX as well, and you can always convert from one format to the other. So SBOM are usually considered as part of a supply chain security strategy, but before looking at how we can generate them and work with them, I'm interested in understanding better why do we need them. Because sometimes it's just, okay, it's part of the auditing process. We want to get the check that we've done that. But if we are not actively using them, it really doesn't help with security, right? So we have this inventory of all the software components. That's great. We want to check for security vulnerabilities. Once we have the inventory, for each of them, for each of the components, we can check, is there any known vulnerability I need to be aware of? So we can do vulnerability scanning. That's already a great help for our strategy. Then we can validate the licenses as well. So is it an open source license, or are there some constraints I need to be aware of? Am I in violation of any of the policies? So I can do that if I know the list of all the components in my software. I can also find outdated components, because for each component in the list, I can check upstream if there's any newer version. Might be nice to know. And I can also verify the integrity. So I can get the digest, the original digest for each of these components and make sure that the dependency that ends up in my final artifact has not been tampered with. All right, that's why or how we can use SBOM. But how do we generate them, and especially when? Because if we consider all the steps in a supply chain, depending on where we generate the SBOM, we're going to have slightly different information. So think about baking cookies. If you note down the list of ingredients at the beginning of the process, you might include not only the ingredients that end up in the final cookies, but also perhaps all the tools and other stuff you have laid down on the table that you're going to use to bake those cookies. In the Java example, it could be maybe your test dependencies. They won't end up in your final artifact, but it's still something to consider. So if we generate the SBOM at the beginning of our software supply chain, we're going to have a very comprehensive list, but it won't be too much useful if what we want to achieve is the list of what ends up in the final artifact. So if we do it a bit later, then we're going to have a more clear overview of what ends up in the final artifact that we deploy in production, but then we're going to miss out on some other dependencies along the chain that might have an impact on the security of the artifact. Because even if it's test dependencies or build dependencies, perhaps if there is any malware or any vulnerability there, it might impact the final result. So I'm going to show just one example, generating SBOM as part of the build life cycle, because it's also one of the most interesting part as developers, especially because with CycloneDX, we get a Gradle and the Maven plugin. So we can add the plugin, and then we can make the SBOM generation part of the build life cycle. And the same thing happens with Maven. But let me show you. So I have the same application as before. It's a Spring Boot application. I'm using the CycloneDX plugin. Same thing will work in Maven. And now I get a command that I can use to generate a bill of material. CycloneDX BOM. And there's a similar command in Maven. So what are we getting now is a JSON file. Let's have a look down there. This is how a software bill of material looks like. So it follows this CycloneDX format. It's a standard specification. And if we have a look at one of the first components, so we have this Spring AOP library, we can see the version, description, we have all the hashes we can use for verify the integrity. We have the license, Apache 2, it's open source. And then we have this package URL. This is an important piece of information because it's what vulnerability scanners use in order to check if there's any vulnerability associated to any of these components. So at this point, we have to do something with this SBOM. So as part of the pipeline, you might publish it somewhere. You might use a scanner, for example, Trivi. Let's see if I can make that bigger. Zoom. Maybe a bit more. Yes. So Trivi is a vulnerability scanner. It's an open source tool. So I can pass an SBOM and then get the list of vulnerabilities. So let's do that. The file is inside build, reports, and then I have the JSON file. And I will check all the components and find any vulnerability if any known vulnerability exists. Now it's updating the database for vulnerabilities. Let's give it a second. But in the meantime, I want to show you something else because I'm using Spring Boot, in particular Spring Boot 3.3. There is a new feature that automatically configures the CycloneDX plugin for you. So every time you build a new Spring Boot application, you get an SBOM. You don't have to configure it explicitly, as long as you add the plugin. On top of that, you can also expose and serve the SBOM as part of the application through an HTTP endpoint. In Spring Boot, we have this project, it's called Spring Boot Actuator, that provides a lot of different management and monitoring endpoints for your application, like Prometheus metrics, health information, configuration information. You can also expose the SBOM. So I have to enable that endpoint, of course. So I enable the SBOM endpoint, and now if I run the application, let's do that. I'll be able to see my SBOM directly from the application. Of course, this is something I want to do in a really careful and controlled way. I don't want to expose this information to everyone. And just like any other administration endpoints provided by Actuator, I want to protect the entire subset of endpoints so that we can only use it internally. But the application started, so let's have a look. Let's see. It's down here. Okay, so Trivy is done, so there's no vulnerabilities. Nice, I'm using the latest version, so I'm happy there is no vulnerability. Let me build the application as a jar file. When I do this, Spring Boot will automatically generate the bill of materials and include it in the final jar file. So now when I run the jar, and the jar is inside the build folder, it's running. Now if I go to Actuator/SBOM up there, I get a list of available bill of materials. By default, you have one, the one for your application. So if I use this ID in the URL, I get the bill of materials. It can be quite convenient. Of course, you might want to do much more than that with the bill of materials, because there are different ways we can use it. So I mentioned Trivy, so you can make it part of your pipeline and scan it for vulnerabilities, scan it for licenses, but you can also use a tool to manage supply chain security risks at a higher level. So this is a tool called Dependency Truck. It's an OWASP project. It's open source, and also very interesting. It's implemented with Java, so it's really great. You can deploy it as a Java application or as a container on Kubernetes, whatever you want, and you can use it. It's all based on software bill of materials. You can use it to do different types of tasks related to supply chain security. Of course, one of them being vulnerability scanning, but also policy enforcement, license compliance. Let's have a look. We have the project that I just built. It's not very interesting because there are no vulnerabilities. I want to show you something a bit more, interesting from this point of view. So I used a different application with a lot of deprecated libraries. So just to get some vulnerabilities, up and running. So we can see that there are a bunch of components as part of the application. These are all the components that come from the SBOM, just in a more, human readable format. We can see a flag if there's any newer version of a dependency detected, which might be interesting to know. We can see the license and if there's any vulnerability. So let's have a look at that. We have 8 vulnerabilities. Now, it might seem that this application is really bad. We even have a critical vulnerability. So what do we do with that? This is the important part. Because it's not enough just to know there is a vulnerability, but we have to do some kind of auditing process here. So this library, snake-YAML, is quite interesting. It's used by Spring Boot to read your application configuration from a YAML file. And there is a vulnerability here in this version that if you deserialize the JSON, the YAML file in a certain way, then you're vulnerable to injection attacks. However, it happens that Spring is not using that method. It's doing it in a safe way. And my application is not using snake-YAML. So it's only used for one use case by Spring in the correct way. So yes, it's a critical vulnerability, but my application is not vulnerable to it. So I need a way to communicate this to my colleagues, to the security team in my organization, to the customers. Because if I'm shipping my artifact, my application, together with an SBOM, I need to also inform them about the vulnerabilities that I found here and my assessment about that. With the upcoming EU Cyber Resilience Act, also in Europe, it seems like we're going to get a need for supplying this software bill of materials, just like it happened in the US last year. So it's important to deliver not just a list of components, but also this assessment. I can do it from this tool, so I can say, hey, I'm not affected, so press the warning. The justification is code is maybe code not reachable because we're really not using that. So there's no way to expose that to that kind of attack. And my response as a vendor, so I want to inform the consumers of my application, is that will not fix because I'm not vulnerable to it. Of course, I'm going to update the library in the next version, but there's really nothing to be worried about. And I need to provide that information in a standard way. So together with SBOM, we can enhance an SBOM and including this information in a standard way using VEX. VEX is a vulnerability exploitability exchange. So if you look at the definition, it's a vulnerability document designed to complement a software bill of materials. It informs users of a software product about the applicability of one or more vulnerability findings. So vulnerability scanning is really important, but the way we handle the found vulnerabilities is even more important. And unfortunately, there's no 100% automated way to deal with that. So there is some kind of human intervention assessing the situation, because then we can determine, am I affected or not? If I am, I have to also inform in a standard way all the consumers of my application what I'm going to do about it. And VEX is one way of doing that. So we can enhance an SBOM with this type of documentation. And the tool I used, again, is dependency track. It's all focused or based on SBOM. So it really shows how much powerful an SBOM can be. So it's not just a checkbox on a security process. It's not just having an inventory list, but it's mostly about how we're going to do with that information. All right. We talked a lot about dependencies. We talked a lot about all the libraries, components, inventories, vulnerability scanning. But at the end of the day, we need to go through this build process that exposes us to some more aspects of supply chain security. Because it's not just about all the libraries we use in our application, but it's also about the whole build environment and how we're going to package together the application. I briefly showed an example with Spring Boot in packaging a Java application as a jar file, but this works for any kind of application really in Java. We can always package it as a jar file, and that's it. We deploy it on a JVM, but that's not the only way to package an application. We could achieve a native executable with GraalVM. So when we talk about GraalVM, there's a lot of attention on almost instant startup time and reduced memory consumption. And that's fantastic, especially if you're using the cloud. We can save money. We can adopt serverless architectures because the application starts really, really fast. But there's one other feature of GraalVM that sometimes is a bit kept aside in this discussion, but it's really, really relevant when you talk about security. And it's that with GraalVM, we get a native executable which has a reduced surface attack compared to the jar file. Because what happens? In a jar file, we find all the dependencies there. So even the code that is not executed, the code that is not called by your application is still there. So if any part of that code, unused code, gets a vulnerability, you might still be vulnerable to it, even if you're not using that part of functionality. But what GraalVM does while compiling to a native executable an application is it starts from the main method in Java, and then it only compiles all the things that are reachable from the main method. Everything else is discarded. So it means that just by going through this native compilation process, we're actually protecting ourselves from some vulnerabilities. Of course, it's not enough. We have to consider all the factors, but at least we can be protected against vulnerabilities affecting all that code that we are not using and that is not useful for our application, because it's simply discarded away. And then we can also build OCI images. Of course, we can do it in different ways. Now, the way I like building container images as a developer is called Cloud Native Build Packs. It's a tool to convert source code into container image, and it works no matter the language or the framework. The good thing for me as a developer is I don't have to write a Docker file. I don't have to be responsible for whether the Docker file is secure, is using best practices in terms of the security, the dependencies that we're fetching from the underlying operating systems. I don't have to deal with any of that. I have a tool that, given my source code, it builds a production-ready image. And if I'm using Spring Boot, like in my case, it just comes out of the box with the Gradle or Maven plugin. I don't have to install it. Same thing with Quarkus. So it's quite convenient. Because, as I mentioned at the beginning, security is not just about tools. We have to consider also the practices and the people. And especially when we talk about developers, even though I'm fine, I could write a Docker file, I don't want. I want to focus on the business logic. And this is also good for the platform team that might want to centralize control over how you containerize applications. So they can deal with all the underlying security operating system stuff. And as a developer, I just get the result. So I can quickly get the container image, and I don't have to be worried about putting in production something that is not secure, because I might not be that much skilled into all the details of how to build a container image, because I'm more into the Java part and building new business logic and producing value there. So it's just to have this separation of concerns. One important feature of cloud-native build packs is that ensures reproducible builds. What is a reproducible build? So yesterday, I had this application. I compiled it and I packaged it using build packs, and I obtained a container image. I haven't changed anything in my application since yesterday. What happens if I run the same process again? So if the source code is the same, I would expect the image to be the same. And usually that's not what happens. Cloud-native build packs instead has this reproducible build feature out of the box. So no matter at what time I build the image, if the input didn't change, the output will not change. And that's really important. I want to have that kind of provenance and traceability also in how things are flowing through my supply chain, software supply chain. Let me show you an example. I have my usual application. Oh, let me stop this one. So I can run the task directly from the Spring Boot Gradle plugin, or from the Maven one, or Quarkus. You also have this similar command from the CLI. Now it will build a container image for me. Besides being a CLI or a plugin for Spring Boot, there are different ways to work with build packs. So for example, if you're deploying on a Kubernetes environment, you can even use build packs as a service using something called kpack. So we have a configuration file like this, where we define a resource named image, where we point at our Git repositories. And every time a change is detected, then a new image is built automatically. It's another option if you're working with Kubernetes. But now we got an image down here, so I can try running it. Port 8080. And before testing the application, I want to show you something that might be interesting, because if we inspect the details of that image, we can see that it was created 44 years ago. That's something weird, right? I mean, I've just built it. So why is that? So 44 years ago, that was actually a conventional date that is used by build packs. It's January the 1st, 1980. But why is that? So imagine having the actual creation timestamp here. If I build the image twice, I will obtain two different images, because the timestamp, at least the timestamp changed. So in order to ensure reproducible builds and not having any source of non-determinism, this is what happens. This is the trade-off. Now you might wonder, yeah, okay, but I want to know when an image was built. There are other ways. I'm gonna show that in a minute. But just be aware, this is the, every time maybe people start using build packs, then they see this date and it can be confusing. But that's the reason why. It's because we want to achieve reproducible builds. Now, if you really don't care about reproducible builds, you assess in your own company strategy that is not a property you need, you can always turn that feature off and still rely on all the other features from build packs. So that's an option. You're not forced to have this behavior. It's just a flag you can pass in the build step. But now the application is running, and it's the same application as before, but I want to show you that now I can customize the SBOM endpoint and getting not just the application software bill of materials, but build packs also includes bill of materials for each layer of the image. So I can get information about everything else that is included inside the image. For example, the JDK. We can see here we're using Bellsoft Liberica JRE version 21. So I can get access to all the bill of materials that are packaged in the image. And I didn't have to write that in my Docker file. There was no Docker file. It's all out of the box. And just to show you, there was a customization of the endpoint. So I had to tell Spring Boot, hey, find this bill of materials inside the image. So I added some additional configuration pointing to the files that are part of the image. All the code is on GitHub, so I'll share with you later. All right. So we're getting almost to the production stage. We got some artifacts. Now I built an image. Would you feel confident now taking this image I've just built and run it on your own production environment? Maybe not, I hope. If you're trying to do, or if you're thinking of doing that, please don't do that. I won't take any responsibility for what's inside. The problem is that you won't really be sure where that image comes from. So maybe we can sign it. We signed the commits, so why not signing also every step in the build process? We can use a tool called cosign, and we can, first of all, sign all the binaries. It might be the GraalVM native executable, it could be a jar file. I want to sign it. So I'll sign it with my own identity, so you'll know that something has been built by me. I also want to sign the image if I'm building an image. And I want to sign SBOMs. Now, the SBOM could come from the jar file, could come from the OCI image. If you're using GraalVM, you can even get GraalVM to generate automatically the software bill of materials for you. There is a flag you can pass to enable that. That's quite convenient. So if I do this, or let me do that, so we can test it directly. So I have the image. Now I'm gonna tag it and push it to my, where is it? Like that. So I want to push it to my GitHub container registry. So maybe you can use it. Extra space. All right. Let's push the image. Now I'll be able to sign it in a second. And the signature will also end up in my container image. So it will be associated to the container image, which is quite convenient for you to try that. And while it's doing that, let's point out the problem with that approach. Even if I sign the image, you still don't know where it's coming from. I mean, I've just built the image in front of you, but you don't know what's inside exactly, right? So how can we solve that? How can I make you trust my application? So I have to provide you with some information about what ended up in my image. What was the source code? What's the commit ID? When did I build it? Where did I build it? In which environment? Did I use Gradle? What kind of Java version? Were there any other build dependencies? So in order to solve that problem, there is a framework called SALSA. It stands for Supply Chain Level for Secure Artifacts. And it's all about ensuring the integrity of the artifacts. And the main concept around this SALSA framework is, once again, this concept of provenance. It's like when you go to the supermarket, like I'm from Italy, so if I go to the supermarket and buy, let's say, oranges, I can probably see that they come from this specific farm in Sicily, they have been approved, and that information is also authenticated, so I know I can trust that those oranges come from that specific farm in Sicily. I want to do the same for software, and SALSA allows to do that. In particular, if we focus on the build process, we can have 4 different levels. Level 0 is we are not doing anything about it, and we have to deal with it. But level 1 is the artifact has provenance showing how it was built. So probably I can write up on a document all the steps I made in order to build an artifact and share it with you. You won't know if you can trust that document because it's just a random document, but at least there is some documentation, but not good enough. So maybe we can go up to level 2. The build runs on a hosted build platform that generates and signs the provenance itself. So I'm not building it on my computer, I'm building it maybe on GitHub. So you can probably trust it more than my own laptop because we don't know what's running, what's available in my laptop. But also I want the build platform itself to generate and sign the provenance. So it's not me as a developer doing that. It's the platform that certifies what is happening on that platform. And once again, that's great. As a developer, I don't want to deal with all those details. But of course, I want to be aware that what I'm building will eventually be trustworthy, right? And then level 3 is an even higher security level because now that provenance is also non-falsifiable. So the build platform offers strong tamper protection. So the good thing is using a platform like GitHub or GitLab, we get this out of the box, so I don't have to be worried about that. I can use the Salsa project, has a generator that you can use in GitHub. Recently, they also introduced a feature in GitHub. So if you're using GitHub Actions, you actually get an even easier access to all this capability. So again, as a developer, I like it. I can keep focusing on my code, but then I get the platform to certifies the build and the provenance for me. So we have the image, so we can sign it. So I can say, let me copy the tag. I can say cosine sign, yes. So now cosine will generate an image signature for me. This is the keyless approach that I mentioned earlier. I haven't defined any key pair, but I can use my GitHub account, for example, to log in and authenticate. So Sigstore will use that. It's a keyless approach. It's really convenient. Also, it reduces the risk of losing your key or exposing your key. And there it is. Now, the image has a signature. So the last point is verifying all this information. That's the deployment part. We want to verify the signatures, of course. We want to verify the Salsa provenance. And if we share that information about the vulnerabilities, for example, with Vex, about what we are handling and what is not affecting our application, we also want to verify the vulnerability report. And there are tools to do that. I mentioned these two. We have Cosine for all the signature-related concern, and then Salsa for the provenance-related concerns. So depending on where we are deploying the application, we could make this validation in our pipeline, or we could make it also in Kubernetes. If you have a policy engine and you're running in Kubernetes, you can apply that. So let me go through an example. We have the image that I published. So now I can use cosine to verify the signature. Let's do that. All right. So there's a lot of information, but what I'm interested in here is this one. The cosine claims were validated. So the signature has been validated. The certificate was verified using trusted certificate authority certificates, and also the existence of the claims in the transparency log. So everything has been validated. So the signature is authentic. So at least you know that it was me with my GitHub Actions pipeline building this application. You can see I'm pointing to my GitHub account for that. And then I also need to verify the Salsa. I can use the Salsa verifier tool from the Salsa project. Let's run it. So this is to verify the provenance. And if we look at the content that we get back, first of all, the Salsa provenance is verified, but now it's here that you get all the information, including when a specific artifact was built. So this is where you get the timestamp, because this provenance is strictly related to that specific artifact. You get information about the pipeline configuration that they used on GitHub. You get information about the time. You get information about all the environment settings that were available on my project. So you can have more information to then make a decision about whether you want to trust my application and run it in your environment. Supply chain security is a shared effort. So we are all in this together. Today, I focused on some tools and strategies for application developers, but it's not just us. So it's a collaborative effort. As I mentioned earlier, people are an important part of the supply chain security strategy. So we need the platform people on board, the security people, everyone that is involved throughout this process from initial source code up to the deployment needs to be aware and needs to contribute. But as developers, we can do our part. And as we saw, it doesn't mean that we need to get a bad experience from it or having, too many more responsibilities. But using tools like build packs, for example, or relying on platforms that support Salsa provenance and signatures out of the box, we can keep focusing on our business logic, our application, but then we get something that can be trustworthy, something that can be trusted by our consumers and by our customers. That was it. Thank you very much. You can find the source code on GitHub. That's the QR code. So we have time for one question. And then for the rest, I'll be outside so you can ask later. Yes?
about your first approach with the shared repository. To me, it sounds like there's a security team auditing your dependencies. If you have your vulnerability scanners in place in your CI/CD pipeline, what's the basic added value of a shared repository other than securing your own machine?
Yeah, so I'll repeat the question briefly. So the question is about what's the value of having maybe a central team in your organization maintaining a central repository and using it as a mirror also to Maven Central and other upstream repository if we are also doing vulnerability scanning as part of each application pipeline. Yeah. That's correct, right? So the additional value is that you have a single point where you can control what is coming inside your organization network from outside, from the internet. So in particular, if you are getting artifacts from different repositories, it's good to have that kind of centralized approach depending on the strategy. And that kind of complements also the vulnerability scanning itself. So one thing is vulnerability scanning, but the others is also which sources from the internet do we trust. So I see them as complementary, like these two things, but both needed based on the strategy.
I'll ask the next question later.
Yes.